Hello again. Here we are again with a BIOL3465 Tropical Forest Ecology and Use lecture. This lecture is on fire and how it affects the local distribution of tropical ecosystems. So I'm going to take a look at fire, and there's fire in an ecosystem. Unfortunately, a fairly common sight in Trinidad. If the dry season lasts for a couple of months or so, you will get fires like these running through even a primary intact tropical forest. How they start and so on, we're going to get into during the course of this lecture, and we'll finally take a look at what it means, what fire means for tropical rainforests, such as what we find in Trinidad. So we're going to go through what are fires, how do fires start, what are the mechanics of a bushfire, how do fires propagate themselves, and so on. We're going to take a look at tropical rainforests and fire, how fire occurs in tropical rainforests, if it does or if it does not. And we're going to take a look at tropical rainforest and after fire. So what happens to the tropical rainforest after fire has passed through. So let's move straight along to the mechanics of fire. Right, so what is fire? Well, we all know what fire looks like. We've all seen fire. We've all lit a match and put it to something to burn. But what is fire? Fire is basically the visual light representation of the oxidation, the rapid oxidation of some material in the presence of the atmosphere. Okay, so what happens with the fire that we see is usually the ignition of some sort of biofuel, usually some sort of carbohydrate, something like methane or some other carbohydrate gas, which is released by organic matter, and somehow it is ignited. Okay, so an extra burst of energy is needed to start a chain reaction where this carbohydrate gas just keeps on burning, oxidizing, releasing more energy, which in turn causes the oxidation of molecules, which in turn causes the releases heat and causes the oxidation of molecules. And we see fire as visible light because at least some of the energy is released as visible light. So we can define fire as the ignition of flammable gases, usually carbohydrate type gases like methane, released by biofuels, and biofuels would be organic matter, most usually in the case of natural ecosystems, plant material like dead organic matter, like leaves and so on heating. So fire is the ignition of flammable gases released by biofuels on heating. Okay, so the ignition of these gases releases more energy, so adjacent fuels are dried out more and release flammable gases that ignite in turn. Now, that chain reaction, because it is a chain reaction, can only proceed, and the emission of flammable gases can only proceed if those biofuels have first completely dried out. They've completely gotten rid of all their moisture, because moisture will be emitted with a raise of energy in the biofuels through that heat first before the flammable gases. Okay? So a prerequisite for fire is that the biofuels must be dry. Okay? Because the first thing which comes off the biofuels is moisture, and that does not burn. It's only when all the moisture is gone that the flammable gases begin to be released and emitted, and those are the ones which can burn. So that is why wet material does not burn. Okay? Fire also needs the biofuels to be distributed contiguously. What that means is that the fuel is adjacent to one another. So when one patch of fuel or one piece of fuel ignites and releases a lot of energy, a lot of that energy is transferred to the next bit of fuel, and that energy drives off all the water and releases all the flammable gases, which can then ignite. Okay? If those patches of fuel or pieces of fuel aren't next to one another, then the heat does not transfer over to drive off the flammable gases and release the flammable gases and ignite. So the fuel must be close to each other so that it can cause that chain reaction. So here are some pictures of fires. These are fires in tropical rainforests. As you can see, you have a front along which the fire is burning, and behind it the organic matter on the forest floor is burnt, and in front of it is this organic matter which is waiting to be burned. You can see a similar sort of thing there. Notice how this log is not burning. It's simply too big for the fire to heat up enough to drive off the flammable gases so that it will catch fire. Okay, so it still retains a fair amount of moisture in it, and it's simply too big to be heated up. These leaves and so on the forest floor are small enough to be heated up, and so perpetuate that chain reaction. Here's a schematic of how a fire starts and how it is propagated. In this first graphic here, we have rain falling on the leaf litter. So these crosses down here are all leaf litter. This is rain, falls on the leaf litter and wets it up, and the leaf litter will remain wet until when the humidity is greater than 65%. When the humidity is greater than 65%, there's too much moisture in the air for the water to evaporate from the leaf litter. Okay? So there's no flammable gases coming off this leaf litter because the water is still present, and that's what will be released first. But the water isn't being released because the humidity in the atmosphere in the understory of the rainforest is still very high. Okay, so this is the normal state of affairs. This is what occurs in a tropical rainforest 95% of the time, and in intact natural rainforest 95% of the time, because the humidity is above 95%. But when the humidity falls below 65%, around about 65%, then there isn't enough moisture in the atmosphere to prevent the water evaporating from the leaf litter. And this little diagram shows that. No more rainfall. So the leaf litter is not wetted up, and the humidity begins to fall. So during the dry season, this situation may occur in a tropical rainforest after a few days or a few weeks. Okay? Generally in a tropical rainforest, if you have rainfall every so often, it's going to keep the leaf litter moist and the humidity high so that you won't get a low enough humidity to dry out the leaf litter. But there may be a few days during the dry season in an intact forest when the humidity falls low enough and the leaf litter can dry out. So these blue squiggles indicate all the water being driven off that leaf litter. Till eventually, once all the water has been driven off that leaf litter, the combustible gases begin to be given off by the leaf litter, and that's what these little yellow arrows indicate. Combustible gases being released from this leaf litter. Okay? And these combustible gases can sit quite happily above the leaf litter until it rains again and no fire can occur. Okay? Because these combustible gases cannot ignite spontaneously by themselves. They need some source of ignition. So there needs to be some ignition point. If that ignition point occurs, then these combustible gases will begin to oxidize or burn, and heat will be released, starting the chain reaction where more of the combustible gases begin to burn, heat is released, more begins to burn, heat is released, and so on, in that chain reaction which I was telling you about. If the leaf litter is contiguous onto this stage now, then the fire begins to spread from one piece of leaf litter to the next. Okay, as the fire advances, more heat goes ahead of it and drives off any remnant amounts of water and starts to evolve these combustible gases, and so the fire will tend to propagate along the forest floor. Okay, so these flames would propagate along the forest floor. Wind helps a lot, and wind will help a lot by transferring more of the heat sideways into the next piece of leaf litter. If there's no wind, a lot of the heat will just go straight up because hot air rises and be lost to the drying effects of on the leaf litter around it. So wind helps that propagation of fire. Okay? So describing that in words, wind helps propagate the fire by lateral direction, or lateral blowing of the heat released on ignition, so that the heat is transferred to adjacent fuels, heats it up, releases combustible gases, and ignites. And the wind will push the heat again sideways, and so the wind will help propagate the fire through the understory. Uphill slopes also aid propagation of fire, okay, because you're always going to have some vegetation above the ignition point, so the heat is going to be much more effective in drying out adjacent fuel and propagating uphill. Conversely, downhill slopes will actually hinder fire, because a fire must be hot enough for the heat to spread downhill when a lot of it is going straight up. So fires will quite often only burn downhill when there's enough wind to blow it downhill. And if there's no wind, fires, if they're small enough, will not be able to burn downhill. Okay? The moisture content of the fuel needs to be low enough, as I said before. If the fuel is too moist, then combustible gases are not evolved from the fuel, but water is. And there needs to be some sort of initial ignition of those combustible gases. In the past, in natural ecosystems, this initial ignition was quite often provided by lightning. Okay, so a lightning storm may occur, and particularly if it's a dry lightning storm, no rain, then a lightning strike may hit the ground and cause a shower of sparks, and those sparks may fall onto the forest floor, and that will be a point of ignition. So the combustible gases will start burning, heating up the adjacent fuel and propagating through the understory. Now, lightning can occur at particular times of year. I was up in Florida a couple of years ago during the summer, and it was amazing how much lightning would occur every day in and around Orlando, where we had taken the kids. So it was no surprise to me to learn that the natural ecosystems around Orlando and down through Florida were dominated by fire. They burnt very regularly, and the natural ignition source would have been lightning. Lightning also occurs in tropical rainforests, and so would have been a natural ignition source of fire. However, it doesn't occur very often, okay? And as we'll see in a minute, fire in a tropical rainforest, through lack of ignition source and also lack of amount of time where humidity is low enough, is very, very intermittent. Ignition sources are much more likely to be provided by human activity. Okay? Humans love fire. It is one of their primary tools. So fire is used very often, and humans have learned how to make fire, and they can often carry fire with them. So whenever you take a look at the fossil record, or the palynological record, or the pollen record, which builds up in swamps and lakes and so on, where pollen of grasses or other pyrophilous or fire-loving plants, where the pollen of grasses increases dramatically, you can usually tell that humans have arrived in that area. So some of the studies, the pollen studies done in lakes in North and South America, consistently date the arrival of humans at a particular date of about, I think it's about 6,000 million years before present. 6,000 years before present. Okay? So human presence dramatically increases the prevalence of fire in an area, mainly because humans provide ignition sources. Okay? Through fire, which they can carry or which they can start. So humans and fire tend to go together. Okay? Let's go to fire in tropical rainforests now. Right, there's a lot of fuel to burn in a tropical rainforest. TRF means tropical rainforest. But most observed fires tend to only burn on the ground in tropical rainforests. Okay? So, like those pictures I showed you before. And those types of fires are very low intensity and will only burn the loose leaf litter on the surface of the soil. The majority of other organic matter is simply too wet for fires to burn. Even so, these fires can affect the ecosystem by killing off small seedlings. Okay? Now, normally humidity in an intact tropical rainforest seldom falls below about 70 to 80% throughout the year. So 70 to 80%, if you remember our point at which leaf litter will start burning out, is usually around 65%. So 70 to 80% is too high for leaf litter to start to burn. So humidity in intact tropical rainforests seldom falls below 70 to 80%, so the leaf litter seldom dries out enough for it to burn. So humidity must fall below 65% to allow fuel to dry to a point where it is combustible. Because of that, fire is not common in tropical rainforests. Okay, fire is not unheard of in a tropical rainforest, and studies which looked at charcoal in the soil profile in tropical rainforests found that fire does occasionally pass through a tropical rainforest, but only between 600 to 1200 years between fires. So fire return times, or the time between fires in an intact rainforest before humans arrived, that was between 600 and 1200 years. So fires were very, very infrequent. Okay? The biota, therefore, of a tropical rainforest, the plants and animals of a tropical rainforest, were not used to fire because they didn't need to be, because fire visited those ecosystems so rarely. The disturbance of tropical rainforests by human activities, however, alters the tropical rainforest immunity to fire, and it does this in two ways. In the dry season, humidity in selectively logged forests fell below 65% for approximately half the time. Now, why did the humidity fall below 65% in the dry season in a selectively logged forest? And the reason is that the canopy has been opened up. Once the canopy is opened up by cutting trees and letting them fall and having more gaps out there, then you will tend to find the humidity in the understory is much lower. So because the canopy has been opened up by selective logging, humidity tends to be much lower for a longer period of time. So during the dry season, the period during which humidity falls below 65% is much, much longer. That gives a greater chance of an ignition source occurring when the combustible gases have been evolved from the leaf litter. Okay, just a couple of pictures to relax your eyes a bit. Both of intact tropical rainforests, trying to make the point that these are very humid and moist, wet environments. Look at the trunks of these trees. They're just covered in moss and lichen. So that moss and lichen needs very high humidities to survive. All of these plants in here are all green and moist, and they're not going to burn. It's only the stuff on the leaf litter on the forest floor which may burn. Humans also increase fire in a tropical rainforest by providing a source of ignition. Okay? And when humans colonize an area of rainforest, quite often they will clear away the trees and plant crops which will allow them to support a larger number of people. Okay? So people will open up the canopy either through selective logging or slash and burn agriculture. They will remove the trees, and that reduces the humidity to below 65%. But not only that, humans and the presence of humans and human activities, particularly agriculture, would provide fire, a source of ignition. So whenever humans arrive in a tropical rainforest, they quite often bring with them the fire. And if the humidity has been below 65% for an appreciable period, there will be enough leaf litter which is dry enough to emit combustible gases and to burn. And this is particularly the case where cleared areas in tropical rainforests. So humans may clear a patch in a tropical rainforest to plant some crops. This reduces the humidity around the margin of the gap, and not only that, fire which is set to clear grasses and weeds in the gap can get into the margins of the rainforest, so that these gaps which are cleared in tropical rainforest can start to expand, almost like a growing saw. Okay, and this is known as edge decay. So human creation and maintenance of savanna or grassland ecosystems in tropical rainforest areas tended to increase the area of savanna. And this is not a recent process. This has been going on for thousands of years. As I said previously, in northern South America, there's a large savanna in northern part of Brazil, in Venezuela, and it spreads into Guyana as well, called the Grand Savanna. And pollen records show in lakes which occur on the savanna that the whole area was forest before humans arrived. But when humans arrived and brought fire with them, the whole area started to convert into savanna vegetation, grassland vegetation. So humans will tend to increase the incidence of fire in tropical rainforests, and in particular places convert the tropical rainforest into savanna or grass areas. And not only that, maintain them in grass areas for long periods of time by increasing the amount of fire which occurs in that ecosystem. Okay? If the fire returns every 2 to 3 years in that ecosystem, trees are not going to get the chance to grow tall and shade out the grasses. So the grasses will dominate the ecosystem and a savanna will be maintained. So here's a picture illustrating what I was saying. A human may carve a small plot out of the rainforest. They will use fire to clear that area. The edge effects around this patch will cause the humidity to be much lower than it normally would be in an intact forest because of the edge effects. And this fire acts as an ignition source. Maybe sparks would fly into the forest and can further cause fire in this tropical rainforest. So some figures. Dry season fire is possible in a savanna only after a day without rain, 24 hours without rain. It takes 5 to 6 rainless days for humidity to fall far enough and long enough for leaf litter to dry out enough to burn in a selectively logged forest, and twice as long as that in a second growth forest, and probably longer than that still, maybe up to 2 weeks in a mature primary forest which hasn't been touched. So as you can see, the longer or the quicker the forest dries out, the longer it's going to be in a state which can burn if there is an ignition source. So there is a greater chance of burning the more an ecosystem is disturbed, and that's what humans do. There is a concern that loss of too much forest cover, particularly in the Amazon basin, will alter rainfall patterns and can accelerate the conversion of forest to savanna. What that means is that the Amazon forest, the rainfall has been studied, and through the use of stable isotopes of oxygen, they're able to say where the moisture, where the water came from, whether it was evaporated from the oceans or whether it has been transpired by plants. And in the Amazon basin, they've calculated that up to 80%, or more than 3/4 of the rainfall which falls on the Amazon basin actually has its origins in transpiration from trees within that forest. So the moisture is therefore cycling in that forest. Okay? So if you cut down that forest, it dramatically decreases the transpiration rate, and that means the amount of rainfall is also going to go down. If the amount of rainfall goes down, then the chance that the remaining forest will burn will rapidly increase. And if that remaining forest will burn, then it won't transpire, and there will be a reinforcing effect, which means that more and more of the forest will be destroyed through fire, through excessive dry seasons, less rainfall, more intense dry seasons, and so on. So there is a concern that once the Amazon basin forests are cleared above a certain threshold area, then there will be a dramatic collapse of the remaining rainforest as it becomes too dry during the dry season to resist human started fires. Okay? So, in a tropical forest, most primary species are killed by fire. They are not adapted to fire at all. Okay? So, let me make that smaller again. So most forest species are killed by fire. If the fire is like those understory creeping fires, then it's mainly seedlings which will be killed. The canopy won't be opened up, and the forest will not change that much. Okay? At least to the naked eye, it won't have changed very much at all. But seedlings and regeneration would have been killed during that fire, and the forest will need time to recover that. Okay? If the fire is dense enough and heavy enough, okay, and middle story and upper story trees are killed and burnt, and the fire, God forbid, gets up into the canopy, the whole canopy is opened up. And in that case, all the trees are killed, and the forest is completely altered, both structurally and compositionally, both in terms of the types of species and the structure. The forest is opened up, and secondary species will come in, or pioneer species will come in, or what we would call R-selected species would come in to the forest area. We would say that the forest has been secondarized. So only secondary species and initial pioneers will remain. All the primary stage, all the K-selected species, a lot of them have been killed by the fire if it is heavy and dense enough. Most importantly, the canopy has been opened, and that actually makes a second fire more likely. When the canopy is opened up, as we said before, it tends to reduce the humidity for greater periods of time, and the leaf litter will dry out faster, and therefore a second fire is more likely. And a second fire can be, in some ways, even more disastrous than the first, because a second fire is much more likely to be hotter, because things will be drier, okay, and it will kill the resprouting seeds or the resprouting trunks and so on of species which survived the first fire. Okay, so a second fire would be even more disastrous. So the changes in a forest may only be temporary. Even if the fire is severe, if it is protected from a second fire, the canopy will soon close again, humidity will be built up, and the ecosystem will be more resistant to fire. If, however, another fire comes through and maintains that open canopy, kills off more of the species, then that forest is likely to be changed forever. So diagrammatically here, if we have a intact tropical forest and it burns, and it's quite a severe fire, so a lot of the mature trees are killed off. So what we have is a structurally altered ecosystem. Okay, 2 incidences. If there is no fire for 100 years, many of these species will be able to continue to grow, close the canopy, and create an ecosystem which was indistinguishable from the first. If there is a next fire, on the other hand, many of these species will be killed, and you would lose the species which can grow tall and close the canopy. Instead, species which can survive a fire begin to predominate. So you would start to get grasses on the ground and shrubs which can survive a fire. Okay? And in this case, this ecosystem will be more prone to fire because the canopy is open and things dry out more. So here's an example of a gap in a secondarily logged tropical forest. You've got pioneer species growing up in there, but this just shows an open canopy, and under this gap the humidity will be down around 50 to 60%, and the leaf litter would have dried out and be ready for burning. Contrast this with the closed canopy forest, very much wetter underneath, a lot more moist vegetation which never dries out and is going to be very resistant to any sort of ignition source because no combustible gases have been evolved, and a lot of water needs to be removed before this understory would dry out enough to burn. This actually looks like a secondary forest, but because the canopy is closed, it is much more resistant to fire. This forest, on the other hand, the canopy is very open, so it's going to dry out more and be much more vulnerable to fire. So if you get repeated fires, it's going to lead to bigger and bigger changes in the composition of the ecosystem. Seeds and root sprouts are progressively eliminated as the subsequent fires destroy them, and species will tend to be lost from the ecosystem or extirpated from the ecosystem before they can reach a size which is big enough for them to seed and reproduce. The K-selected species, which grow slowest, will be the first to be lost. Okay? If the structure breaks down further and the canopy opens up even more, you'll start to get grasses invading, which can survive fire very well by retreating to underground rootstocks, and so they actually favor fire. Okay? So in Trinidad, what is going to happen in the future with fire? Well, we have one of the highest population densities of people in Trinidad, and with a large population density of people, there are more ignition sources, and more ignition sources means more likelihood of fire. Okay? There's going to be more fires in the areas where dry seasons are more intense, so it's no accident then that you tend to get more fires during the western parts of Trinidad and fewer fires in the eastern parts of Trinidad. Repeated fires will eliminate species from an area and encourage grasses. So you will get patches much like behind Tunapuna there, where the area is repeatedly burnt and now only has grasses. A fire savanna is what that resulting ecosystem is called. And on top of, behind Mount St. Benedict there, with all those pine plantations, they were planted on top of fire savannas as a attempt to try and return those fire savannas to a forest. In Trinidad, global climate change is most likely predicted to lead to more intense dry seasons. Now, more intense dry seasons means that the rainforests in Trinidad are more likely to be vulnerable to fire. So there's going to be more chance of an ignition source coinciding with a period of time when the understory is dry. So there's going to be much more likelihood of fire with global climate change, more intense dry seasons, higher population density, so there'll be more chance of fire in Trinidad. And it's my opinion that fire is probably the biggest threat to the remaining forests and natural ecosystems in Trinidad today. Okay? It's not so much clearing for agriculture, clearing for development. It's very much one. Clearing for quarrying is pretty bad as well. But increased intensity of dry season and a high population density will mean that there's going to be much more fires. Trinidad is a microcosm of the tropics, and more intense dry seasons are predicted for much of the tropics. So large amounts of fire is predicted for many of the last remaining large blocks of rainforest around the world. Already in Southeast Asia there have been extensive fires in Borneo, one of the islands, the large islands in the Indonesian/Malaysian archipelago. And this occurred in Southeast Asia during El Nino years. Now, El Nino is a period where you would tend to get much more dry, intense dry seasons. El Nino years are predicted to increase in frequency with global climate change and global warming. So it's already looking at vast tracts of tropical rainforests in Southeast Asia and the Amazon basin may collapse because they're no longer pumping water into the atmosphere, there's less rainfall, and there's therefore much more chance of fire passing through that ecosystem. With increased fire, there's going to be more carbon released into the atmosphere. More carbon released into the atmosphere will exacerbate global warming and then increase the amount of dry seasons and therefore increase the chance of burning. So there has been predicted a reinforcing effect in the collapse of these tropical rainforests. More carbon, less rain, or more seasonal rain, and therefore more fires. We're just hoping that this prediction will not come to pass. And it's one of the reasons why scientists are so concerned about limiting the amount of global warming. If we can restrict it to around 2%, or 2 degrees, above turn of the century levels, then we may not get into this feed-forward reaction. But if we go over 2%, all bets are off, and nobody is too certain what is going to happen, and we may see images like this more often. So these are the fires in Borneo, burning over a large area and engulfing large areas of forest in these big, large fires which getting up into the canopy and killing all the trees in the area. So in Trinidad, what can we do? Well, fire is the big problem, so voluntary firefighting units to prevent and stop fire is probably needed. There needs to be some sort of method to stop ignition sources when the fire risk is at its greatest. So maybe a graduated fire risk system, which is broadcast to the general population to say, okay, the humidity in the understory is below 65%, and it has been for 3 days, so therefore the risk of fire in this tropical rainforest is very, very high. So the forest officers can get out into the forest en masse and prevent people providing ignition sources which will form the fires. Once fires have started, there needs to be some sort of fire monitoring and early warning system, so the minimum amount of bush can possible will be burnt. But unfortunately, forestry division people and people who don't want fires to happen cannot be around all the time. So in the end, we must educate the general public so that they know that if they set a fire or ignite an ignition source in a tropical rainforest during the wrong time of year, then that forest will burn down. Education, therefore, is very important. So, thank you very much. That's our lecture on fire. Please come prepared next week.